Dear students, welcome back. So we have already started the quantum free electron theory of metals, and we have seen the classical theory within that, and we have also seen the failure of the classical theory. So the main point in the classical theory is electrons of the metal are just going to behave like a gas, and therefore it obeys the kinetic theory of the gases, right? And from that we had made certain derivations of the conductivity, and the conductivity will be coming as sigma is equal to ne squared tau by m, where tau is your relaxation time or mean collision time, right? M is the mass, E is the charge of the electron, and so on, right? If we have applied that formula on the let us suppose on the case of the temperature. So theoretically what we know, as the temperature is going to increase, the conductivity decrease, right? This is a practical approach. The practically we know, right? As if you would let us suppose you have taken any current cutting wire, and there you measure what is the value of the current, and there you go to go on increasing the temperature. So as you will go on increasing the temperature, you will find the conductivity will go on decreasing. So it is directly inversely proportional to the absolute temperature. But if we are going to apply the classical theory, what we observe that it is not inversely proportional to temperature, rather it is inversely proportional to the square root of the temperature. See, similarly we had other failures like on the dependence of the total number of the valence electron or the conduction electron. Then we have all the specific heat. So there were many failures which classical theory could not satisfy. So therefore, to resolve that, we require a new theory, and that theory came from the quantum theory of the free electrons, right? And this is what we are going to look into this lecture, right? So now let us start the quantum theory of free electrons, right, for the conductivity in case of metal. Now let us see the introduction of the assumptions of the quantum free electron theory. As we had the classical theory, assumptions of classical theory, here also we have the assumptions of the quantum free electron theory. So how we came to the quantum free electron theory assumptions? So let us see some part of this. Sommerfeld proposes this theory in 1928. So 1928 he has proposed this theory, retaining the concept of the free electron moving and the uniform potential within the metal in the classical theory, but treated the electron as obeying the law of quantum mechanics. So in the classical theory we had seen the electrons are free to move, and those electrons we had called as the valence electron or the conduction electron. So Sommerfeld also retained that, right? So the electron is able to freely move within the crystal, but they are not going to randomly going to occupy the space. The energy of those electrons are going to be quantized. So the law of the quantum mechanics was applied over here. How it was applied, let us see. Based on the de Broglie concept, he assumed, that is Sommerfeld assumed, that the moving electron behave as if it were system of waves. So electron, as you know, electron is a particle. So moment it is going to move, it will have the wave, and that wave is called the de Broglie wave that we have already seen in the quantum mechanics. So what he said, so when the electron is going to move, it is not going to behave like a gas particle. It is going to behave like a wave. It is called matter wave, as we know, which is associated with the moving particle. Let's see next one. According to quantum mechanics, the energy of the electron in a metal is quantized. That I'm going to tell you in the detail. That is the moment you are getting a wave. So you have also seen in the electron in one-dimensional box. So if the electron is going to move to the different energy state, it will have got the different value of the energy, and that is called your eigenvalues. That we have already seen in the quantum mechanics also. So what we are saying, according to the quantum mechanics, the energy of an electron in a metal is going to quantize. So if this, let us suppose in the metal, the free electrons only we are talking. If the free electrons have got the different energy, it is going to be quantized. It is going to be available in the different energy state. It is not going to just behave like a gas. It will not be randomly moving. right? He realized the role of the Pauli exclusion principle. I will tell you, or you may be knowing from your school education, but in the next slide I will tell you what is the Pauli exclusion principle. Here he realized the role of the Pauli exclusion principle in restricting the energy's value of electrons. So that also I will take up. The theory proposed known as the quantum free electron theory. So occupying all those things, if we are going to consider all the above points, so he gave a new theory, and that theory is called quantum free electron theory. The main assumptions of this theory are as follows. So let us see what are the main assumptions. First, the energy level of the conduction electron are quantized. So it does mean if we have got the n number of the electrons, all the electron may not have the same energy, right? It may have the different value of the energy. So it is going to be fitted into the different levels, that again I will be taking in the next slide, and therefore this energy is going to be quantized. It is not random energy. Second, the distribution of the electron in the various allowed energy level occupy as per Pauli's exclusion principle. So we have the n, let us suppose n number of the energy state. So in which energy state which electron will go? So it will go as per the Pauli's exclusion principle. Again, I am coming back on the Pauli's exclusion principle, showing you in the next slide. However, the following assumptions of the classical electron theory continue to be applicable in the quantum free electron theory. So these are the two exclusive theory. Firstly, what you are saying, the electrons are going to be quantized. Secondly, we are saying these electrons are going to be distributed into the different energy state following the Pauli's exclusion principle. But the two theory, number 4, the electrons travel in the constant potential inside the metal but stay confined within its boundary, which is the part of your classical theory. It continues over here also. Both the attraction between the electrons and lattice ions and repulsion between the electrons themselves are ignored. So there also we have seen that is you have the lattice where you have the positive charge, and then you have the electron. So naturally you should have the electrostatic force of the attraction, or between the two electrons you should have the electrostatic force of the repulsion. So whatever the potential is getting generated because of these forces, the electrical conductivity is independent of all these potentials. So this is again applicable in the quantum theory also. Now how to take up all those things and then satisfy all the failures, right, which we have seen in the classical theory. To understand this, we have to understand few more things. So now let us see few. Firstly, let us see what is the Fermi energy. Right here only I am going to explain you what is the Pauli's exclusion principle also. Due to quantization rule, a material in a solid state possesses a set of allowed energy levels. Right. Again I am coming back. So what you are saying, due to quantization rule, a material in solid state possesses a set of allowed energy state. Let us suppose you have any metals and you have the thousands of the atoms there, over there, right? So according to the available number of the atoms over there, right, we'll have the or number of the electrons over there, right, in the total electrons that we are taking, that is we are talking about the conduction electron. We'll have certain number of the fixed energy state. What will be that? See the number, point number 2. For a metal containing n free electrons, if they have the capital N free electrons, there will be n such allowed energy levels. So as many number of the electrons you have, that many number of the energy level will also be there, which are separated by the energy difference that are characteristics of the material. Now let us see this diagram. Now what we said, let us suppose we have the capital N number of the free electrons. So this is the capital N number of the free electrons. So if you have the capital N number of the free electrons, you will have the capital N number of the energy states. So all these lines that you are saying, all these your horizontal line, all these lines are your energy state. All these energy states are separated by a very small difference of the energy. That is, as you can see, the different electrons will have the different value of the energy. So the electrons will not have the same value of the energy. It will have the different value of the energy over there. Now, how many electrons is going to be where in which energy state? That also we require to see, and that is exactly called Pauli's exclusion principle. What we say? The allowed energy value for the conduction electron in the metal are also quantized, are related to the energy level of the metals. So it's the same thing that I explained you. That is here electrons are going to be distributed. The allowed energy level for the conduction electrons in the metal are also quantized. That is how many number of the allowed energy state will be there. So that is also quantized, right? And are related to the energy level of metals. All right. As per the Pauli's exclusion principle, each energy level can accommodate maximum of 2 electrons, one with the spin up and another with the spin down. Now you see, this is the Pauli's exclusion principle. We have n number of here. This is your n number of the energy state. If you have the n number of the free electrons, you have got the n number of the energy state. So in each of the energy state, starting from the first one, first the electron is going to the lowest energy state. So the electron will be going here, lowest energy state. Now you know the electrons will have the two type of the spin, which you say spin up and spin down. So the electron which have got the lowest energy, right, will go to the lowest energy state, and here it can have only 2 electrons. How many electrons? Only 2 electrons. It can be, each energy state can be filled up with the only 2 electrons. So how filling is going to occur? It is going to occur from the lowest energy state. So electrons having the lowest energy will be coming to the lowest energy state, right? And here the 2 electrons, one will have the opposite spin up, another electron will have the spin down. So like here, this is what I have represented. So in one energy state, 2 electrons are going to be occupied according to the Pauli's exclusion principle. So naturally, if you have capital N number of the free electrons, and then as I told you, if you have the capital N number of the free electrons, then you have the capital N number of your energy state also, right? In each energy state, 2 electrons are going to be there. So all the electrons are going to be exhausted with the energy number of the energy n by 2, because n number of the energy state you have, and in each energy state 2 electrons is there. So half of the energy state still remain vacant where there is no electron. All right, this is distribution at 0 Kelvin, where we have not given any temperature. That is, from our side we have not given any temperature. Then the highest energy occupied by the electron. So what is the highest energy? Naturally, this line, the topmost line, is your highest energy, and this highest energy occupied by the electron at 0 Kelvin will be known as the Fermi energy. So to understand this quantum free electron theory, we require to understand the Fermi energy. So this is the Fermi energy. Let us see the diagram of the Pauli's exclusion principle. So what we say, how the electrons are going to be distributed. You must have seen this diagram in your school also. So for n equal to 1, this is your principal quantum number, as you know. So here you have the 1s, right? For n equal to 2, here you have the 2s, right? So each of them you have the 2 electrons. For n equal to 3, third energy state, you have the 2p and 3s, right? So here 2p also, you have the electron, 1 up, 1 down, right? And 3s also you have the 1 up, 1 down. This is how they make the pairs. So let us see how they make pairs. So this is your increasing energy. So what this is, that I have taken this line, vertical line, is with the increasing energy state. So first you are saying 1s2, right? So what you have taken here, you have taken the 2 electrons, one with the spin up and the with the spin down. Then what you are taking, 2s2. So what is again here there, 1 spin up, 1 spin down. Then you say 2p6. So how 2p6 has made, 1 spin up, 1 spin down, again 1 spin up, 1 spin down, again 1 spin up, 1 spin down. So this is how the electrons are being filled up in the different energy state, and this is how we say the electrons are quantized. So all those electrons which is freely available in the metal are not moving randomly. They are highly quantized. So we know what is the energy of the electron and where it is available, right? Similarly, for the third energy state, what we can say, it is your 3s, one up, 1 down, and then again you have the 3p6. So 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. So this is how the electrons are distributed, and this is called your Pauli's exclusion principle, right? So anyway, so what we say, the electrons are distributed by using the Pauli's exclusion principle, which says the electron are going first in the energy state which have got the lowest energy, right? Let's now again the same figure for your reference. The allowed energy value of the electrons are realized in terms of the occupation of the allowed energy levels under the certain rules. So what are the certain rules? This is what I have explained in the previous slide. When filling up the energy level is undertaken, the universal rule apply that any system which is free tends to go to the lowest energy state which come into the picture. So from where it is going to start? It is going to start from the lowest energy state. So filling up anything which is free, it will be going first into the lowest energy state. Next one. Thus, a pair of electron, one with a spin up and other with the spin down, occupy the lowest level. Okay, already explained you. Next pair of the electron occupy the next higher level, and so on till the electrons in the metal are accommodated. So till it is all the energy state is going to be filled up, or the all electrons are going to be exhausted. This is how the electrons are going to be distributed. However, there will be many allowed energy level available for the occupation of the electrons. The energy of the highest occupied level at 0 degree absolute 0 degree absolute is called Fermi energy, and the energy level is referred as the Fermi level. The Fermi energy is also denoted by EF. So what I told you, the highest energy occupied by the electron at 0 Kelvin. So this is the electron which have got the highest energy, and this energy state we will call your Fermi energy. So the highest energy occupied by the occupied level at the 0 degree absolute is called Fermi energy, and the energy level is referred as Fermi level. All right. So let us go with this. So when there is no external energy supplied for the electron, such as the thermal energy or the electrical energy, the electrons are free and thus settle in the lowest energy state available. So in this way, this is how they have settled, provided we have not given any thermal energy or electrical, any type of the outside energy we have not given. Thus, at the temperature of the absolute zero, when metal is not in the influence of any external field, the energy level lying above the Fermi level are empty, right? And these lying levels are completely unfilled, or those lying below are completely filled. So this is what I explained you. That is, if you have the n number of the free electrons, n number of the energy states will be there, but only n by 2 is getting filled up, right? So still n by 2, half of them is absolutely free, right? And half of them are absolutely filled up with the electrons. This is at your 0 Kelvin. Since there are 2 electrons in each level out of n allowed energy level, so n by 2 of them are going to be occupied, right? So the Fermi level is an energy level midway between the surface of the conduction band and bottom surface of the conduction band, as on the figure that I am going to show you next. The EV, that is the conduction valence band. If EV is the energy corresponding to the top of the valence band, and EC is the energy corresponding to the bottom surface of the conduction band, and EF be the Fermi energy corresponding to them, then this is where you are going to have your Fermi energy, right? So this we are saying, this is your top of your bottom of your conduction band, and this is your top of your valence band, right? So Fermi energy in case of the metal is going to lie exactly in between the conduction band and valence band, and this proof again I will show you, right? Now what we can say, the EF, so for what is the Fermi energy? Fermi energy is this value. So EC plus EV by 2, that is, this is your EC, this is your Fermi energy. So this is your EC, this is your EV. So EC plus EV by 2 is your Fermi energy, because it is lying in between. All right. Now, so what I am writing, what I'm going to do here, I'm going to add EC. So here I have, let us suppose I'm going to add EC and then I'm going to subtract EC. So it should not be any problem. So I have added EC and let us suppose I'm going to minus EC. So if I'm going to add EC, then we'll have the 2 EC. One EC is over here and another EC is over here. So 2 EC and 2 EC is going to be divided by 2. So how much we are getting? We are going to get EC, right? Then what is left? EV minus another one EC is there because one you have subtracted. So how much you have? EV minus EC divided by 2, right? So this is your Fermi energy. So what we can say? Fermi energy value we can say is equal to EC plus EV minus EC by 2, and EV minus EC by 2 equal to what we can say? EG by 2. This is your energy gap. What is this? This value is your EC and this is your EV. If you are going to take the difference between them, then what you are going to get? You are getting this energy gap, right? So this is your EG. So EV minus EC is nothing, this is your energy gap. So we are writing EG by 2. 2 has come from here, right? So what we can say? EF minus EC, EF is here, and take this EC on the left hand side. EF minus EC is equal to how much we are getting? EG by 2. So this is what we are saying, that the Fermi energy is lying exactly between your valence band and the conduction band. Now let us see. At absolute zero, all your electrons is below your Fermi energy, right? So this will your completely, this will your valence band. There is no electron in the conduction band, right? Now as you are going to move the temperature, some of the electron will start moving from the valence band to conduction band. So this is what has been shown over here. So electron have started moving from the valence band to conduction band. Now if you are going to further increase the temperature, that is the temperature is getting higher, now you see the electron is exponentially moving in your conduction band, and therefore the conductivity is going to increase there in that case. So at high temperature, some electrons can reach the conduction band and contribute to the electric current. So in this way you are going to have the electric current. At the absolute zero, you cannot have your electric current, right? So this was the concept of your Fermi level. Now this concept we'll see in the better way using the Fermi Dirac statistics, and that we will be using in the. So now in the next class we will going to see how, if we are going to increase the temperature, how really the electron are moving from the valence band to conduction band. What are the other factors on which the movement of the electrons is going to dependent, and this is how the what was mathematically derived, right? And that is called your Fermi Dirac statistics. So that we are going to look up into in the next class, right? So I hope firstly, before moving to the next class, all of you are going to prepare this classical theory and the quantum theory, the basics of the classical theory and the quantum theory nicely, and if you are getting any doubt, come back without any hesitation, so that you will have the nice understanding in the next class. Thank you very much for your presence.